algorithms parties have like lost and been vanquished and all that kind of good stuff. Data is the most important thing by far. If you believe that people are more important, then to me what you're saying is you believe that Google engineers are smarter than Facebook engineers. Because Google can do a much, much, much better job of predicting what ads people are going to click on than Facebook can. Is that true? No, of course it's not true. It's not even remotely true. Google has a lot better data than Facebook does, right? Does Google have better algorithms? No, of course not. No one does, right? That's sort of the great secret of machine learning. Everyone's using the exact same algorithms. There's only a few that work at this kind of scale that we're talking about, right? Data wins everything. There are these awesome feedback loops in this industry when it comes to developing machine learning algorithms. The people who gather the most data fastest win. All right, so we optimize for speed. Okay. Let's talk a little about ETL. If I say ETL, people know what I'm talking about. This is San Francisco. People might not know. Extract, transform, and load. This is like the sort of dirty underbelly of enterprise data management stuff. This is the unsexy, unfun stuff, right? ETL, data science, and machine learning. Most machine learning algorithms start, obviously most of them start in academic papers. And most of them start with like some parameters or some data set that exists already and is nicely formatted and it's got like some variables and is all nice and clean, ready to go. Right? We just feed that in the machine learning algorithm, out comes money on the other side. It's very exciting. The real world though, we have dirty, disastrous, awful data that's not even remotely ready to go into a machine learning algorithm, right? It's just kind of up here somewhere. And our job as data scientists is to do the legwork, to do really effectively what is ETL, to map that dirty, messy, awful data into the input the machine learning algorithm expects, okay? And if you, like one of the things that's really incredibly beneficial as a data scientist is to study ETL patterns, study patterns people use for building data warehouses, because they are the exact same patterns and the exact same problems you have when you're building large-scale machine learning systems, okay? Common example, Google has a sort of feature on all their queries, like what is the language of the query? Is it English, is it Spanish, is it French, whatever, right, that kind of thing. Google introduces a new sort of extension to that feature. Instead of just being like English, we're gonna go for like sub-dialects. We're gonna go for like English, oh, but it's like Louisiana Creole. Or English, but it's Australian English, not UK English, like that kind of thing, right? What happens to the machine learning algorithm when we introduce these new language tags into the web logs? The machine learning system's never seen these things before. These are brand new features, right? English US, English Creole, English UK, English Australia. We have no data on the performance of these features, and so the machine learning model completely falls over. It totally breaks because an underlying input to it changed. Does that roughly make sense to people, right? This is a very bad thing. This is fundamentally an ETL problem. This is like a change data capture, evolving schema problem, and it's the exact same problem you have when you're building a data warehouse. I teach a data science course. Cloudera teaches a data science course. I teach a data science course sometimes too. And it's so funny to me to see data warehouse architects do really, really, really well in my data science course. It's kind of fantastic. They have a great perspective from sitting at kind of the intersection of the ETL side of things and the business user side of things. They get the questions people are asking, but they also have like the data processing capabilities to be able like to do the coding side of things as well. It's like kind of great. So yeah, ETL is the wax on, wax off of data science. That said, okay, I thought this would have been funnier. All right, never mind. We need to go a little bit beyond ETL when we're doing machine learning. We're really trying to explore the space. Really, explore the space. I watched this like 5 times today. I was just so excited about this reference, and now it's just totally falling flat. I know exactly. Thank you. Yeah, that's what I'm talking about. Most ETL processes, most ETL data warehousing processes, they hate change. Hate it. Can't stand change. The worst thing that happens to an ETL developer, worst thing happens to his life, is some upstream process changes in some way. Some table schema changes, some data pipeline changes. That's a nightmare. It's a terrible thing that happens. When we're doing machine learning systems, when we're doing data science, change is something we love. Change is fantastic. Change means we got a new data set, we got a new signal, some new information came along. So I think it's a sort of situation where our mentality has to shift. We have to like think about how do we optimize our data pipelines and our data processing to be like not just adaptable to change, but eager for change, right? Like anticipating, hoping for change. And you really have to like think about these problems in a very, very new way, and it's a lot of fun to do, right? It's just a very enjoyable process. Just so that we can explore the space of parameters, explore the space of features, you know, really, explore the space. I'm practicing my Christopher Walken, never mind, it's fun. Okay. Machine learning architectures. Change gears a little bit. Machine learning architectures. Software engineers here. You got some software engineers in the room? You got some, okay, right? Yay, software engineers, right? Okay, all right. So I'm trying to think about how to explain this stuff to software engineers. And I have a model, and I'm trying it out for the first time tonight. So like afterwards, if you would like catch me and tell me how it goes, that would be really cool. I would like to know, right? Sort of system style. Yeah, this is great. Yeah. I just like, you Google image search for like awful enterprise architecture diagram, right? Yeah, exactly. Oh my God. This is actually, let's see if I have this here. It's the to-be vision of digital infrastructure of Vermont's learning health system. High-level enterprise business architecture. Yeah, high level. That's the high level, right? It's very high level. Yes, exactly. Just god-awful nightmare. I love this thing though.
It's called coded.
The way to think about machine learning as a software engineer is to think in terms of systems. You should think about machine learning algorithms almost as if they were various options for storing your data, okay? Let's say you have options for like serving and querying data. What are my options if I'm serving and querying data? Relational database, right? That's an option. There's actually a lot of those different ones, right? Search index, something like Lucene or something like that, right? Option. NoSQL store, Mongo, HBase, Riak, whatever one was invented while I was giving this talk, like that kind of stuff, right? Lots and lots and lots of options, okay? Tons of options. If you have a business problem, you're trying to design a system to solve it, you can look at all these options and say, okay, I'm going to pick some of these, and some of these will be good for this, and some of these will be good for this other things, right? And they all have like tuning parameters associated with them. They're all good at certain things, they're all bad at certain things, okay? People know what I'm talking about here when I say this, right? That's the same mentality I want you to have when it comes to machine learning algorithms. That's the same way to think about them. There's a small set of things machine learning algorithms do well. Within kind of each of those broad categories, there are a number of options to choose from. There's Mongo, there's HBase, there's Riak, there's all that kind of stuff. They all have upsides, they all have downsides, they're all perfect for some problems, they're all terrible for some problems, okay? And when you're thinking about solving a problem using machine learning algorithms, you want to take these individual pieces and basically like join them together to form an overall architecture, okay? That's how we're going to think about it. Okay, so what are those things? 3 things we know how to do. It's kind of like simplifies the world dramatically. There's lots and lots of talk in machine learning and academia about like time series prediction, right? Like all this kind of crazy stuff that academics claim they can do. They can't do it. It doesn't work, right? Time series prediction, forget about it. It's over. It's 3 things we know how to do. We're going to talk about the 3 things right now. These are 3 things that like literally, swear to God, promise they really, really work. It's not magic, okay? All right. Along with the 3 things, we're going to ask 5 questions. In the same way you'd ask questions about like, how does your database system respond to lack of indexes, or like how much data can I store in a row of an HBase table? Same kind of thing. There's going to be some questions we're going to ask of every machine learning algorithm, right? When should I use it? What does the input look like? What does the output look like? Very important question, how many parameters do I have to tune? Kind of an ominous question. Like, if you just, someone's talking to you about a machine learning algorithm, you should just kind of stare at them like a really cold, hard stare and be like, how many parameters does this thing have? And the answer is more than 2, I'm going to kill you. That kind of thing, okay? And finally, why will it fail? And everything fails. So why is this particular machine learning algorithm going to fail? All right. Option 1, collaborative filtering. The granddaddy of them all, collaborative filtering. Collaborative filtering is great, all right? Netflix movie recommendations, Amazon recommendations, Foursquare Explorer tab. This is all collaborative filtering, behind the scenes, underneath. It's all collaborative filtering, okay? So what do we use collaborative filtering for? We use it to find hidden structure. I see some subset of the items you buy, or some subset of the items you've rated, and I'm curious what other items belong to that set. What are the other things you bought, or the other things you like, or the other things you'd be interested in that I don't see right now? Collaborative filtering helps me find hidden structure in data sets, all right? The great thing about collaborative filtering, super, super simple input, right? Common separated value file. There's some kind of user, there's some kind of item, and there's some kind of weight that tells me about the relationship between that user and that item. And the whole sort of art, so to speak, of data science is figuring out what that weight should be. You're Netflix, and you have the star rating the person gave the movie. You have whether they wrote a review. You have how many times they watched the movie. You have how many times they visited the page. You have, thanks to social features now, whether or not their best friend has watched the movie. You have all this different stuff, and you need to distill all that information down into one little tiny number that you feed into this algorithm. Here's the bad news. There's no a priori way to do it. There's no right way to do it. You just have to try stuff. Back to, remember, toothbrush floor, right? Toothbrush floor, that's what we're talking about, toothbrush to the floor. The output of the collaborative filtering model is basically item 1, Forrest Gump, item 2, Minority Report, and some sort of score that gives me some notion of the weight between those two. All right, and if I have those sort of matrix of item-to-item relationships, I can generate new recommendations for people as they give me more feedback about how they feel about different movies. All right. What do I have to tune? I have to tune the distance metric I use, like sort of measuring distance between different weights, and the weight calculations themselves. Again, toothbrush, toothbrush, right? Collaborative filtering is going to fall over on me, though, if my input data is too sparse. Okay, so if I don't have enough density between the users and the items, I'm not going to be able to generate anything like good recommendations. All right? I have to get into much more fun, much more advanced matrix techniques at that point. Collaborative filtering on Hadoop is it's actually like one of the things that Hadoop does especially well. In fact, it's one of the things that a project called Apache Mahout does especially well. There's a really, really smart guy named Sean Owen who works at a company now called Mirix that he founded doing nothing but recommender systems. And he wrote the original collaborative filtering library in Mahout that is like far and away the most widely used component of Mahout and is absolutely fantastic for doing collaborative filtering. So we have good options there from a Hadoop perspective. Second thing we can do, we can classify things. We can predict stuff. Will you click on this ad? Yes, no. Will Josh order an Uber cab in the next 5 minutes? Yes, no. The answer is yes, by the way. Actually, I kind of wonder if like Uber has a predictive model to like leave an Uber cab outside my house at like 8 p.m. on Friday. Do you guys do that? I don't know. Internally? I don't know if that's a thing. There's certain kind of like prediction problems that are not really prediction problems. I worked for a credit card company once, and it was basically, we were kind of analyzing like spend behavior, like purchase behavior, right? And one of the predictions the system came up with was, if you shopped at Walmart this week, you will shop at Walmart next week. That's what we call a sun will rise tomorrow style prediction, right? Model is awesome on those kinds of questions. Really good at predicting that. Josh ordering an Uber cab at 8 p.m. on Friday is a sunrise tomorrow kind of prediction. Not very interesting. All right. We can predict things. Random forests. Random forests are glorious. They are wonderful. We love random forests. Huge, huge fan of random forests. All right. So what do we use random forests for? We use them to classify and predict things. What do we need? We need a dependent variable. Dependent variable is the thing we're going to predict. All right? We need a whole bunch of independent variables. Those are the things that hopefully give us some information about the sort of outcome that we're interested in, give us some information about the dependent variable, right? What are we going to build? Random forest, we're going to build lots and lots and lots and lots and lots of little trees. We're going to take this big, huge data set, and we're going to sample from it over and over and over and over again. We're going to grab a little sample here, we're going to grab a little sample there, hundreds, thousands of times, and we're going to build a whole bunch of little decision trees in order to try to predict the dependent variable from a few of the independent variables. All right? We're going to create a whole bunch of really crappy prediction models, like thousands of lousy prediction models, right? And it turns out, through kind of the genius of, I don't know, like math or whatever, that if you do this, if you take a whole bunch of really lousy, like sort of crappy models, and you basically let them vote on any new observation. You ask every little crappy model, hey crappy model, how are you going to do, what should we do for this particular prediction, right? And you just add up their votes, you end up with a great model. A model that actually outperforms most any other model you can come up with. And this whole technique is called ensemble models. And it's been developed in computer science over the last 10 years or so. And it's just absolutely fantastic, right? I mean, there's nothing that makes me happier than thinking about a bunch of dumb people doing kind of something awesome by getting together to vote, right? That's just fantastic. The great thing about random forest too, very, very, very few parameters, which is glorious, right? The only thing we really need to consider is basically how do we partition this data? How do we like create our little tiny samples? And then for each of those samples, how do we construct that tree? how many variables are we going to consider for each of those different trees?